today's lesson has to do with electric field. So what is an electric field? An electric field is a region around a charged object where the electric forces on other objects can be observed. Can we see electric fields? No, but we know that they exist. But it's not something that we can see. So again, what we're going to learn is that when we say an electric field lines produce a picture, this is for us to understand the interactions of things. So again, we're drawing a model to help us conceptualize it. So even though electric fields exist, it's not something that we can observe with our eyes, but we can use particles to help us see the behavior of these electric fields and what they influence. So all charged objects have a region around them where they exert an electrostatic force on other objects, whether those objects have a charge or not. And we observed some of this when we also did our lab. So an electric field is defined by the number and direction of the lines of force. So the lines of force, again, these are imaginary, okay, used to create a picture of the electric field. So again, this is going to be a model, because we know that models help us to understand things. If the electric field lines are close together, the field is strong. The direction of a line of force is defined as the direction of a dimensionless positive test charge that would move if placed in the electric field. So the lines of force will always be perpendicular to the charged surface creating them. So sometimes we have a point charge, sometimes we have a line, so it's always going to be perpendicular. The strength can be indicated by the number of lines of force, and then the direction is extremely important. So let's look at right now if we were to have a positive charge and a negative charge. If I have a positive charge, the lines of force are always going to point out of that charge. If I have a negative charge, they're always going to point in, no matter what. So that's just if I had a charge by itself. Then we're going to look like if we have two charges next to each other. So over here in this diagram, I have a positive charge and a negative charge. Well, I just said a second ago that the lines of force always go out of the positive charge. So these are all going out of the positive charge. But I know between a positive and a negative charge that there's going to be a force of attraction, because unlike charges attract one another. So when they go out of the positive, they go into the negative, because they always go out of positive charges and into negative charges. So this is the way the electric field would look if I had a positive charge and a negative charge. Okay. So one of the questions we could ask you on the test is, I could just not have anything in the charges, and you would have to say, what's this charge? So just based on the electric field lines, or if I could just, let's say I white it out. Let's say this was whited out. I'm just giving you an example. And I would say, okay, here's a diagram of an electric field. What must be the charge here? You would know it has to be negative, because this is a force of attraction. Over here, I have two like charges. These both have to be positive. So number one, the field lines are going out. But because they're going out and we know that they're repelling one another, you would say number one, the charges have to be the same, because there's a force of repulsion between them. Number one. Number two, they have to be both positive charges, because the electric field lines are coming out. So this could be a question on the test where you don't have what these charges are, and that's all you see, and the question would be, what is the charge of the two particles? They're both positive. And you could tell just by looking at the electric field lines. So the two things are, number one, it's a force of repulsion. Number two, because the force lines are coming out, you know that they're both positive. And then at the end of the notes, I think I put the part showing the other ones. I should have put with the two negatives, but we'll look at that. So first of all, electric fields are real, but the field lines are imaginary. This is exactly like magnetic fields. If you learned about magnetic fields in like astronomy or another class, we know that magnetic fields exist, but again, you can't see the lines. But the picture helps us to see what's going on. So when two charged objects get farther apart, the attraction or repulsion between them becomes weaker, and we know that mathematically by looking at the equation. Because when we calculate the electric field using Coulomb's law, F is equal to K Q1 Q2 over R squared, as that R in the denominator increases, we see that the electric field is going to get smaller. Well, that's for the electrostatic force. So now, to calculate the electric field intensity is the ratio of the force exerted by a field on a charged particle and the charge on the particle. So again, this indicates the strength of the electric field that is affecting the charged object at a certain point within the field. So E, that's electric field intensity. Now that's equal to the electric force, which is Coulomb's law, divided by the point charge. Now remember, this is measured in newtons. Charge is measured in coulombs, so the unit for electric field is going to be a newton per coulomb. So the electric field is a vector quantity. Remember, vectors have both magnitude and direction, so we're going to have to indicate the direction of the field. So the direction at a point is defined as the direction of the electric force that would be exerted. So basically, once we find the direction of the force, that'll be the direction of the field. So here's an example, a positive test charge. So again, we're going to write our given, we're going to write what we want to find, we're going to write our basic equation, we're going to rearrange our equation to solve for the unknown terms unknown, substitute and solve. So it says a positive test charge, so that's Q, is placed in an electric field. The force acting on it, so here, that's my F. What is the electric field intensity? So I want to find E. So E is equal to F over Q. And because this is at 10 degrees, that's going to be the direction for my electric field at 10 degrees. So what do we do to find, here's our steps. So number one, to find the electric field for more than one charge, we're going to have to apply the principle of superposition. This is easy. What happens if I have, again, more than one charge? So we're going to have vectors, and what do? We're going to do just like we did before. We're going to make our table, right? And we're going to add it up, and that's what we're going to do. So first, calculate the electric field produced by each charge. So you're going to have, let's say, E1, E2, and E3. Then what you're going to do is you're going to then, if there's only two, you would add them head to tail and find the resultant. If you have three, you would find the x and y components, add up all the x's, all the y's, and then find the resultants just like we did before. So you can apply the principle of superposition to many different things, and it's just math. You know the only new physics that we're learning today? The only new thing that we're learning today, physics-wise, besides the diagrams, is this right here, this one equation. So now when we apply the principle of superposition, we're applying the principle of superposition to electric fields. Okay? Now this is an example in your book, and I'm going to work an example for you in the homework, so I'm not going to work this step by step because number one, I don't like the way they do it, so we'll do it my way. So it says, anyway, what happens here is you have one electric field here, E1, and one electric field here, E2. But because electric fields are the strength here, because these are vector quantities, I want to find the resultant. So what you can do is you could add these two head to tail and find the resultant. Or I could find E1x, E1y, E2x, E2y, add them up, and then get EX and EY, use the Pythagorean theorem, EX and EY just to get E total, and then find both the magnitude and direction. And that's what we're going to do. We'll do it this way because it'll be a lot easier. So that's the example in your notes. And the last thing we're going to talk about is the Millikan oil drop experiment. So there was actually a famous American physicist, Robert Millikan, and this kind of shows what he did. So he used a modified pair of charged parallel plates to measure the charges on microscopic oil droplets. So he actually got this oil droplet to be suspended between these charged plates. And what was he able to do? Why is he so famous? And I'm sure you learned about him in chemistry, without a doubt. And what he did was he was able to calculate the electric charge. So he found out that the charge, the smallest elementary charge is 1.6 times 10 to the negative 19 coulombs. So when we say the charge on an electron is negative 1.6 times 10 to the 19 coulombs, and we say the charge on a proton is positive 1.6 times 10 to the 19 coulombs, this is the man who was able to find this out. So this is an extremely important experiment. So again, he suspended this tiny oil droplet between the two plates. So he found out when the oil drop is suspended, the weight is equal to the electrostatic force. So it's actually things that we've done. So it's like drawing a free body diagram here and saying that the force of weight is equal and opposite to the electrostatic force. See this? And that's how he was able to calculate this. And so his conclusions: the oil drop must have a number of excess electrons on it, giving it its charge, so it's suspended. And then the charge on the oil drop can be determined because the electric field intensity, E, is equal to VD. And we're going to do those calculations in the next chapter. Just to summarize the chapter, and here's some more of his, this is again how he found out what the charge is. And that's like probably one thing for sure that you learned in chemistry. I did a little on the end after I did the notes. I realized I didn't do the other diagram. So this is a review, because when you take your test, you're going to see diagrams like this on the test. Okay? So again, this is the way the electric field looks between two positive charges. This is the way it looks between two negative charges. So you see the difference that between two negative charges, if I whited out the charges, and I said, okay, what are these charges? You know they're positive because they repel one another, but the arrows are going out. This one, they're repelling each other as well, but the arrows are going in. So you know these are negative and these are positive. These are positive and negative because there's a force of attraction. So on your test, some of your multiple choice questions, and this is standardized test questions, is they just show you diagrams like this, and you have to identify the charges. But that's easy enough. And then here, the electric field between two oppositely charged conducting plates. So if I had a positive plate and a negative plate, we're going to see that the electric field, the lines, always go from positive to negative. Why do they go from positive to negative? They always go out of positive, and they always go into negative.